SPS Intern Symposium. I'm really happy to start off things. My name is Brad Conrad. I'm the director of the Society of Physics Students and Sigma Pi Sigma, the Physics and Astronomy Honor Society. And I am extremely excited to hear all the wonderful talks that we have prepared for today. There's a couple of remarks we'd like to have from everybody. So first, I'd like to welcome Alexander. You want to come on up and make remarks on behalf of George Washington University?
Okay, thank you very much, Brad. My name is Alexander van der Horst. I'm the chair of the physics department here. And first of all, I wanted to welcome you all. We're very happy to have you all here and very much looking forward to all your presentations. I just wanted to say a couple of things about the building that you are in. Because I don't know if you have noticed when you walked in here yesterday or today, there are some big plaques outside. One of George Gamow, who was a professor here. You don't know, George Gamow was famous for many contributions to physics. One of them was kind of the man behind the Big Bang Theory, the actual physical theory, not the TV show. He, when he came here, he wanted to have Edward Teller come here, also a very famous physicist. And he also wanted to have big conferences here where he would bring all kinds of physicists from all over the world to talk about the things that were happening in physics. And because of that, in 1939, and there's another plaque here on the building, Niels Bohr announced the splitting of the uranium nucleus, which then started the atomic age. I don't know if people here have seen Oppenheimer already or are planning to do so. Please don't talk about this because I'm going to see it tomorrow. Spoilers. Kind of know what happened historically, but I still want to enjoy that. But there's a lot of that kind of history here, and actually George Gamow's desk is still in the building on the 4th floor. We have it in the visitor office. If anyone would be interested to get a little bit of Gamow juice or vibe or something, we can all go upstairs there maybe this afternoon, take up pictures and stuff. But I think one thing, and that's what I wanted to get to, is that Gamow was very well known for being this big famous physicist, big contributions. But one of the things he also did was a lot of popularization of physics. He wrote several books that were for the general public, explaining physics and explaining what was so awesome about physics. And you all as early career physicists and having done these internships this summer, this is something I think that we all should keep in mind once in a while, that we should always keep explaining physics, how awesome it is, and especially these days where sometimes the debates about science go into funny directions, going out there and explaining how awesome physics is and what we can learn from science in general, I think is very important. And so, and today you'll be presenting what you've done this summer, but I would say also in the years to come, keep presenting and keep talking to people about your awesome physics. And with that, I'll hand it over back to Brad. Thank you.
So I would like to acknowledge that the support for all of you has come from a lot of different places. So this program is partially supported by the societies and the organizations that help support the interns. So if you are a mentor of an intern, would you mind standing up for a second? Or if you've helped support interns in the past, would you mind standing up, please? And can we get a round of applause for them? These people spend a lot of time and energy to work with you over the summer, and AIP also is supportive of physics and astronomy students and engineers. All of you are going to go off and you're going to go off into the physical sciences, and you have a physics degree, you're always going to be a physicist, but you're going to go off and you're going to go solve all the world's problems, and you're going to end up in all these crazy places you never would have thought possible. So I just hope that you remember the support that people have given you here today, and that this is always a home base for you. You are SPS. You are Sigma Pi Sigma. You are always welcome here, and we always want to have you come back. And if they get a chance in the future to mentor a student or to support a student, I'd really appreciate it. Okay. And additionally, I would like to comment to everybody that's joining us today why this internship is special. So you might notice that we have 17 awesome interns here, and they're in 17 very different placements, and that's on purpose because each intern is working on a unique project, doing something different, but they're all living together and working together here in Washington, D.C., and they get to share their experiences with one another. And that's part of the magic. So if you're a NIST intern, you still know what it's like to work on Capitol Hill. If you're doing science policy, you still know what it's like to do science outreach with K through 12. And that's part of what makes this program really special is no matter what your placement, you get to see what the full breadth of you can do in the physical sciences. And so now I'm going to turn it off to the MC for the rest of the symposium. Kayla Stevens, the Assistant Director for SPS. Come on up.
Yes, I'm your MC. No. So I'm Kayla Stevens, like he said, I'm the assistant director. I've had the pleasure of overseeing the internship program, and I'm so excited. And I'm sure I can speak from everyone, your mentors and AIP, all your supporters, family and friends, and how excited we're about to see the work that you did over the summer. So if you can give me a round of applause for our first presenter, our Soft Matter Society of Rheology intern, Bryn.
Gonna get me emotional over here. All right. Well, good morning. Welcome to the 2023 SPS Intern presentations. How do I open my slideshow? Sorry. All right. So I'm really excited to be here and to be kicking us off today. For those of you that I haven't had the pleasure of meeting, my name is Bryn Schierenbeck. This is a weird little. My name is Bryn Schierenbeck, and I use she, her pronouns, and I am an incoming senior engineering major at Cornell College. I had the opportunity to be this year's Society of Rheology / Soft Matter Kitchen intern, and I will be presenting on the exploration of viscoelasticity using dairy products. So the Society of Rheology was one of the 5 founding members of AIP and is dedicated to applying and advancing rheology. This is their mission statement right here, but I'm sure most of you are curious to know, what is rheology exactly? So rheology is defined as the study of the flow of matter. It focuses heavily on non-Newtonian fluids, which are defined as liquids that do not follow Newton's law of viscosity, which says that stress is equal to the viscosity constant times the rate of deformation, or change in shape. Rheology has a variety of crucial applications in many different fields, including material sciences, engineering, industry practices, pharmaceuticals, what have you. The second part of my internship title is the Soft Matter Kitchen. The Soft Matter Kitchen was created by my mentor, R.F. Nelson, and is dedicated to advancing rheology through the study of food. It's making it accessible so that you can bring the lab directly to your own kitchen table. I spent my summer first familiarizing myself with rheology and then eventually focusing on one of the 4 key aspects called viscoelasticity. Viscoelasticity is a material property that describes materials that behave in both solid and fluid-like behavior. We study it in order to understand when a material is going to react elastically to a certain stress, but then possibly viscously to another. The key to understanding this concept is knowing that it is heavily timescale dependent. Timescale refers to the duration of time in which a stress is applied. As a general rule, built-up stresses within a material will relax over time. Think memory foam. Along with this, shorter timescales result in more solid-like behavior, where longer timescales result in fluid-like behavior. It's important to analyze the material's behavior at both of these points, because sometimes you might find seemingly contradicting results, but you want to get the full picture. In order to help visualize this, I came up with 3 different demonstrations using proto-rheological methods. Proto-rheology refers to observational experimentation that you can do when you don't have a standard rheometer. Pulling, stretching, melting, stirring, all of that fall into this category, as well as specific tests that you can conduct to infer a specific value. For our first demonstration, I have edible silly putty. So silly putty is a common educational tool used to educate on viscoelasticity because of its clear reaction to different timescales. And I actually brought some today so you can see. It's definitely going to make a little bit of a mess, but that's all right. So as you can see, when I apply stress for a short amount of time, it breaks like a solid. But just after I get it off my hands, if I apply that stress for a longer amount of time, stretches and flows like a liquid. And that is timescale dependence in action. Along with that, silly putty is also a great way to demonstrate creep. Creep is a longer timescale characteristic and describes how a material continues to deform under a constant stress, like gravity. You can see this with the silly putty by balling it up and then letting it sit and watching as the diameter expands. This might be helpful to know in things like stability or shelf life, like in cake decorating. On to my next few demonstrations. So I spent the first portion of my summer analyzing the rheological differences between regular cheese and dairy-free cheese. As you can see on one of them, I have all the ingredients listed. That's because I made it at home by myself, and I definitely do not recommend doing this unless you want your kitchen to smell absolutely foul. But anyways, up first, we have the beam displacement test. So the beam displacement test involves placing a slice of cheese between two support beams and watching as the midpoint deflects with time. From this, you can calculate if it's going to be a perfect solid or a viscoelastic material, because if it doesn't deflect, then perfect solid. If it does a little bit, viscoelastic. Here are examples from my own experimentation. As you can see, the potato base was almost a perfect solid, but to the naked eye. The regular deflected a lot, and the cashew was relatively in the middle. This might be helpful to know for things such as, actually, I already said it, shelf life. We're good. Now we have the infamous bounce test. And I say infamous because it became quite common for, instead of people asking me how my day was or what I was working on, they would just skip straight to how are the cheese balls? And I think for at least a good majority of the interns here, this is all that they knew about my internship. So I'm excited to provide some background and show how this has more value than beyond just entertainment. But basically, the bounce test uses the drop and rebound height to solve for a value of tangent delta. And tangent delta is defined as the ratio between two moduli, the energy loss modulus and the energy storage modulus. And we can use it to determine where a material lies on a range of viscoelasticity. So if your tangent delta approaches 0, it's an elastic solid. And if your tangent delta approaches infinity, it's more near liquid. These are my cheese balls bouncing in the background. Here's a more in-depth diagram. As you can see, the potato base behaved the most solid-like, again, but this time the cashew and the regular cheddar were switched. This highlights the importance of looking at both short and longer timescales in order to get the full picture of the material's behavior. And this also might be helpful to know for short-term, this is a short-term timescale analyzation, and this might be helpful to know for like chewing, using utensils, stuff like that. For me, it was fun to prove that cheese is indeed viscoelastic, because you didn't inherently know that before these experiments. But you can prove that by literally playing with your food. So that was fun. Final thoughts. Rheology, like I said, has a variety of applications across many different fields. And it can be used for, like, engineers want to know what their material is going to behave like when designing a structure. Pharmaceutical industry heavily depends on this kind of research in order to insert anything into our bloodstreams. And in terms of our mission at the Soft Matter Kitchen, understanding rheology and viscoelasticity has everything to do with how the food gets onto your plate. Using simple demos and simple ingredients, we hope to expand the study of rheology as a whole. And I'd like to take just a second to thank all of you guys, Brad, Michaela, Kayla, and everyone here at SPS. I had an amazing summer, and I'm not going to regret it. So thank you guys so much.
Okay, time for questions. We have time for 2 or 3 quick questions. Yep. Okay, who's got a question?
Any questions?
Questions?
Bryn, I saw
Yes.
on the slide that you had where you had the 3 cheeses across 4 feet.
Yes.
I noticed they're different thicknesses. So do you think there would have been a different result if the thickness of each of those cheeses had been the same?
No, because they're in the equation, it takes into account density, length of the suspended portion, and the time elapsed. So it's all, and the volume. So it's all taken into account. Good question.
Other questions? So I have one.
Yes.
So what's causing the sagging?
Gravity.
Okay, so okay, second follow-up. So gravity causes the sagging. What is gravity doing to the cheese-like products? So like what's happening in the material?
Oh, are you talking about on the microstructure?
Yeah.
Okay. So basically, viscoelastic materials are you guys familiar with polymers? They're like long chain-like molecules. Basically, what's happening is that these microstructures are getting pulled apart, and so the chains are extending and allowing for a little bit of sag. Is that?
Yep. So the polymers are stretching and moving around.
Yep. Cool. They're just rearranging.
Round of applause for our speaker. Come on up. Next speaker.
Next, we have our APT intern, Melissa. Please give a round of applause for her.
Go ahead and change your time.
It's here.
Should be on the Google.
It's already there? Okay. Oh, there it is.
Good.
Thank you. Good morning, everybody. My name is Melissa Cano. I attend the University of Texas at El Paso. I'm a senior and I'm majoring in physics, minoring in secondary education. My mentor is Justine Heron, and my presentation is The Art and Science of Teaching. So teaching physics. Physics is a fundamental science that requires the nature of matter and space and time. Effectively teaching physics requires a balance between the art of engaging students and the science of conveying complex concepts. Now, can I get a raise of hands on who plans to pursue PhD physics at the PhD level? Most everybody, right? That's great. So with that being said, that means that you will have to teach physics at some point in your career, whether it be in a government facility lab or as a professor to your undergrad students. This summer, I have researched the art of teaching physics, and I have narrowed it down to some points, which would be engaging pedagogy. You need to be able to captivate your students' interest by demonstrations, interactive hands-on experiments, as well as activities. You need to be able to have effective communication, to be able to have a clear explanation and adapt your teaching techniques to those diverse learning that your students might have. You also need to be able to cultivate curiosity. You need to be able to ask questions, explore concepts, and develop a genuine interest for students for physics. Now, the science of teaching physics. You need cognitive science, where you apply learning theories to enhance your lessons. You need to be able to implement formative assessment during your instruction to gauge students' understandings and make timely adjustments. And you also need to implement physics education research to inform and apply it in your teaching practices. So what is PER? PER is the study of how students learn physics and how teachers effectively teach these physics concepts. The mission is to research and understand the best ways that students can grasp the physics topics and improve their overall learning experience. Now, the way you can integrate PER in undergraduate studies is by curriculum design, so aligning your content by these research-based practices. You can also use active learning techniques to incorporate group activities, peer instruction, as well as engaging your students actively. And the most important one for me, at least, conceptual understanding, where you focus the deep conceptual understanding instead of remote memorization, and as well as shifting away from the traditional lecture-based instruction that we currently receive at university level. So over the summer, I got the opportunity to attend 2 high schools here in DC. First, I went to the Thomas Jefferson High School for Science and Technology, where it is the #1 high school in the nation. They have roughly around $600,000 of funding just their science department. And they have everything from quantum lab to an optics lab to a planetarium, an oceanography lab, carpentry shop. It's the teacher's dream with unlimited resources. Then I also visited the Jackson Reed High School, which is the biggest public DC school. And they do have very elaborate programs. Nonetheless, the funding is not as it would be at TJ. I did take the chance to include the demographics, and although this presentation is not based on equity, it does give insight on how resources can really help us expand not just the teachers, but the students themselves. I also got the very big privilege of attending the 2023 AAPT summer meeting in Sacramento, California, where I hosted a 1-hour workshop with teachers, and I collaborated with them about our teaching philosophy about the challenges and successes they meet in every field, in every high school in their region. And we were just fostering a stronger connection between the theory and practice of the field in physics education. I also attended workshops that gave me valuable between the theory and practice of the field in physics education. I also attended workshops that gave me valuable insights on the challenges and successes that teachers face in their classrooms today. And with that experience, I came to the conclusion that physics high school teachers face the same challenges undergraduate physics professors face today. I did want to show you this pamphlet I made for the conference as a resource for teachers to implement physics in their classrooms. It's 3 demos. It's the egg drop, magnets, and rocket launcher. If you remember from high school, those are some of our favorite ones. Now, I'm going to go ahead and talk about the impacts and rewards of teaching physics. Of course, you get to inspire future scientists, and you nurture their interest as well as shape the future for physicists. And the biggest one for me, where you make an impact. You make a difference in the education where you address challenges, advancing in society, and you really do get to live a lifelong journey of exploring physics with students. I am including this quote that is one of my favorites, that says, "Students will perhaps forget what you said, what you did, but they will never forget how you made them feel." And for all of us, for example, if I reflect on my biggest and best teacher that I had in high school, she wasn't even STEM, she was history. And it was just based on how she made you feel in the classroom and her ways of teaching, and most of all, her passion and how she inspired and guided us through the year. My final thoughts. So teaching physics is both a science that requires a lot of passion, creativity, and dedication. When you combine the art of engaging with PER, you can actually create a transformative learning experience to our students. So with that being said, I want to invite you all to work together to inspire the new generations of physicists. I want to go ahead and say thank you to my mentor, Justine Herron, and an honorable mention to Jack, to Brad, Michaela, and Kayla. To my intern cohort, I wish you all the best of luck to your future endeavors, and I know we'll make it very far. Thank you.
Questions?
Sure.
So you mentioned that the physics of high school and DC, what were the big differences that you saw, or what did you learn from doing your physics?
That's a great question. So the one in TJ, which is short for Thomas Jefferson, that high school has a lot of funding. It's unlike anything I have ever seen before. The difference would be that every teacher in TJ has a PhD in their profession. And although it is a public school, it is an admission-based school. So you only get there based on an exam, and that's something that I saw that was very different. Jackson Reed, which is the regular high school, is something that we're more used to. So the differences would be how prepared the teachers are, the resources they have, and the resources students are able to reach.
What lab were you most surprised to see at Thomas Jefferson?
That's a great question. So the lab that I was most surprised to see, I would say the quantum lab, but as well as the carpentry shop. My dad's a carpenter, and that carpentry shop in that high school is almost as big as his facility. So the resources are endless.
Round of applause for Sophia. One more.
You said that high school and undergraduate teaching faces similar challenges. What were some of the larger challenges that?
That's a great question. Some of the similar challenges that both high school and undergraduates face is knowledge gaps, math proficiency, engagement, and time constraint. Just being able to cover all of the topics with physics in depth.
Round of applause for Steve.
Thank you.
Okay. We have our next speaker.
Next, we have one of our NIST research interns. We can welcome Clayton.
Okay, go and get yours up. Yeah.
Hello, welcome. My name is Clayton Marquette. I am from Carthage College in Wisconsin. I was placed at NIST in the Advanced Electronics group, working with my mentor, Dr. Martin Sohn. So this slide may look hectic, but I'm going to walk you through it. This is the setup we used to generate entangled photons. We first start out here with a 405 nanometer laser, where we throw it through a power control, and then through the half wave plate and quarter wave plate, which turns the linearly polarized light into a 45 degree polarization, and that creates a superposition between horizontal and vertical photons, essentially meaning they can exist at the same time. From there, the laser travels to the polarizing beam splitter, where in a classical world, the vertical photons would reflect off of it and the horizontal would transmit. And then from there, we go to our periodically polarized potassium titanol phosphate crystal, where it undergoes a process called parametric down conversion. Essentially, it turns one photon into two by halving the frequencies and doubling the wavelengths. And then the laser travels back to the beam splitter, where again, horizontal transmits and vertical reflects, where we can then measure it at two different ports to determine whether they are entangled or not. And the way we can determine whether they are entangled or not is through the Hohmann-Mandel effect. And essentially that means when they are entangled, there will be an interference between the two and we will not register a coincidence. But this can only happen when there is no delay between the two, as you can see in this graph on the right. Looking back at the polarizing beam splitter on the left, because the two photons coming back to the beam splitter are in a superposition, we cannot say whether they will reflect or transmit for sure. However, in the first two possibilities, we can say that both of them or one of each reflects and transmits because they both come out of the same port, and we can count both photons. However, in the third and fourth possibility, we cannot say what photon went where because we don't know what the polarization was because they are in superposition. And in that case, the two photons are indistinguishable and there's 100% visibility, which means they are perfectly correlated. And this shows quantum correlation. This slide is so you can see where the maximum interference points are going to be between the two of them. The graph the setup on the left shows more of our experimental setup, where we have singular photon on the top and an idler photon on the bottom. But after it comes out of the beam splitter, we cannot say whether it'll be horizontally or vertically polarized. As you can see, the red dots on all four of them, the two of them on the bottom are circled, are where the maximum interference points are going to be. And that is because if you look at the pi over 4 case and pi over 4 case, which is right here, you will see that there is both a green and a purple line coming out to the top right and a green and purple line coming to the bottom right. And you would expect to see a high number of coincidences because they would line up perfectly. However, we don't, which shows you the maximum interference point. Our actual experimental setup is pictured here. The first part, this blue line down to here is the setup you saw on the first slide. And then from there, we put each photon back through another half-wave plate so we can control the rotation and get the sinusoidal graph that you saw, where we can measure it with single photon counting modules and a coincidence counter. And we were able to verify the entanglement in 3 different ways. The first way was graphical. So these are the 4 sinusoidal curves you saw on the slide previous. They're just overlaid on top of each other. And if you note this little orange circle down here, it is the pi over 4 case, or 45 degrees in each situation. And you can see that there is the dip that we would expect to see when they are correlated. Another important fact is the visibilities calculated by the equation you can see on the right-hand side of the screen, where C is the number of coincidences. And because we got visibilities of almost 100%, we can say they're very strongly correlated. The second way we looked at it was visually. So the graph on the left side is going to be changing, and that is our signal photon. And the counter on the right will be counting up to 90 degrees, and that's our idler photon. And you can see as we change the idler degree that the signal photon will also change. And as we get to the 45 degrees, the number of coincidences, or the white dots, will drop to almost nothing. And then as we move away from 45 degrees, they'll slowly return. And the last way we did it was mathematically. So John Stuart Bell mathematically contradicted the hidden variable theory presented in the EPR paper. And that's called Bell's inequality, which is this equation right down here. And a way we can test to see whether Bell's equality is violated or not is to use the CHSH inequality, where you test the S variable to the number 2. If your S variable is less than 2, it's classical and it obeys the hidden variable theory. If it's greater than 2, it's going to be quantum and agree with Bell's inequality that contradicts the hidden variable theorem. The theoretical maximum for the S value is 2 squared root of 2, or 2.82. And the experimental value we got was 2.8177 with a very small uncertainty, which is very close to the theoretical maximum. And that essentially shows 3 different ways that we have verified the polarization quantum entanglement between 2 photons. I'd like to thank my mentor, Dr. Martin Sohn, my postdoc, Yoon Kim, the rest of the NIST staff I met along the way, everyone at SPS and AIP for their help and the opportunity, and of course the other interns for making the summer memorable.
Questions? In the back.
So what was the day, a typical day like in your experience? Can you see these lasers? You have to wear glasses all the time?
The safety reasons we wear glasses all the time. The laser coming out of the laser was like a bluish purple color. But then once the down conversion happened, we couldn't see it. But I didn't spend a whole lot of time in the lab. I did a lot more reading than I did lab stuff, because coming into the summer, I knew nothing about the quantum world. So I spent the majority of my summer learning how to do that.
It's time for one more.
You talked about both quantum entanglement and coincidence, I think, or
Correlation.
And there was one slide where you had like entanglement /
Mhm.
correlation. Can you explain what the difference is between those two?
Yeah, so the physical measurement that we find is correlation, but it's very commonly referred to as entanglement, because when they're correlated, you can't tell like which photon you're actually looking at, because they're essentially identical. So that's why we say entangled sometimes, because the correlation is so high that you essentially can't tell.
Round of applause for our speaker. Okay. Our next speaker coming up.
Our next speaker is also from this, and
I'll let
do a
you-
round of applause for Janessa, please.
Hello, everyone. Let me get this working. Hello. Yes, I was a NIST research intern this summer, and I did modeling the 2 quantum coherent spectrum of a semiconductor microcavity. First things first, a little bit about me. I am a recent graduate. I graduated with my BS in space physics with a minor in computer science from Embry-Riddle Aeronautical University in Prescott, Arizona. Most of my undergrad research was on gravitational theory. I am a 2-time SPS intern. I was last year's SOC intern. This year, I am a NIST research intern. I have also served on the SPS National Council for 2 years, being the Associate Zone Counselor for Zone 16, including Arizona, New Mexico, and Mexico. I currently work with Dr. John Mather and Dr. Brad Conrad on the NASA Starshade program, and I love to read.
So like I said, I did a lot of gravitational theory in my undergrad. So this was a big transition for me into multidimensional spectroscopy. But I learned that multidimensional spectroscopy allows physicists to observe light-matter interactions by analyzing excitonic spectra. So that's exactly what we're doing. We used a gallium arsenide nanostructure to observe the many-body interaction occurring inside the cavity. I was tasked with simulating a theoretical model for a 2 quantum spectra that we see experimentally so that we can compare our results. I did this by going into the polariton basis and using double-sided Feynman diagrams to dissect a set of equations that would help us in our simulation. So before I get too deep into the physics of it all, I wanted to go over some details. So a polariton is a combination of a photon and an exciton. It's very quantum. An exciton is a combination of an electron and a hole. And a hole is basically an atom that's missing an electron where there could exist one. And a biexciton is 2 times that. So 2 holes, 2 electrons. So even though I was mainly theoretical on this project, there was an experimental setup. So we had short pulses exciting our sample and going through a set of nested interferometers, which isolates the nonlinear response. So the multiple time delays gives us multiple spectral dimension. So if we were just looking at the linear spectra or linear response, we would just see condensed spectra like stacked on top of each other, which is why we're looking at the nonlinear response. So what we do see is the lower and upper polariton spectra. So we need a theoretical model because the spectra, as you'll see in a few slides, can be very messy. So we need something to compare our findings and be able to clearly see what's happening and control our parameters. So here is an example of real experimental spectra. This is co-circular polarization. So you can see the upper and lower polariton along the diagonal, and then across the diagonal, you see a mix of the 2. So going into actually building our simulation, I first started by diagonalizing the Jaynes-Cummings Hamiltonian, which is the first equation at the top. So when you diagonalize a matrix, you end up with some eigenvalues along the way. These eigenvalues are lambda 1 and lambda 2. They actually give us our energies for the upper and lower polariton. So I plotted these lambda values as a function of detuning, where detuning is the difference between the exciton frequency and the cavity frequency. So these polaritons travel from left to right. As you'll see in a future animation, the energy increases as detuning increases. So the energies on that last slide follow this level scheme diagram where G is ground, E is the first excited state, and F is the second excited state. A particle can't jump from ground straight up to the second excited state. There needs to be some things that are happening to get there. So it cannot do something like this, but it can do something like this. So in order to filter out these illegal jumps in our simulation, we need to add a matrix into our code. Otherwise, we would just see a whole bunch of peaks not looking like experimental data at all. Here's an example of one of the 2 quantum Feynman diagrams that I used for our simulation. So each of the elements on the diagrams tells us something about the equation, whether it's the direction of the arrow or what side the arrow is on, either the left or the right, left line being the ket, right line being the bra. Basically what we're doing is our system is described by a density matrix, and we are applying perturbation theory to the ket and the bra. So after various approximations and learning a lot about these diagrams, you can get an equation that looks like this. So as a reminder, this is what our 2 quantum spectrum looks like experimentally. So after combining all of those things, you can eventually get something that looks like this. So this is my theoretical model that I simulated with a modified detuning value of -3. If I changed the detuning value to something else, it would just move the peaks around. So here is an animation, so you can visualize the detuning changing, the energy changing with respect to detuning. So in some of our data, in our collinear polarized data, we see another peak. So what is this peak? We think it is the biexciton. You see it in the plot on the right. It's circled in red, so that is the extra peak. So we can add that to our simulation just to get closer with our experimental data. We know that it has an independent energy, so we need to add another level scheme on our diagram and add another filter for any illegal jumps. So here's my animation after adding the biexciton to the simulation. It is moving laterally. Okay, so some next steps that can be done are adding any other options to explain what this extra peak is. So here is a dark state added to the animation with a fixed detuning of -1. I would like to thank SPS National for this great opportunity, the NIST Nanoscale Spectroscopy Group for taking me under their wing, and of course, Jared and Giuseppe for being amazing mentors and supporting me this whole summer. Thank you.
We have time for questions from the exciting talk. Right here.
So I saw on the list of materials needed that patience was on that list. So I'm curious, where do you think most of that resource had to go to on this project?
Coding has a lot of struggles in it, especially when you get too many errors. So I think just being patient with yourself is very important in doing something like this and doing code in general.
How has this internship impacted your career?
Wow, great question. I actually do think I will be going into optics, probably, whether that be pursuing a PhD in optics or going into industry, like doing some optics. So yeah.
Round of applause. Okay, next up, PowerPoint. Go ahead. Is your next one?
Let's give it up for our next NIST research intern, Colin.
Hello and welcome. Again, my name is Colin Myers, and this is Hydrogenating the Surface of Diamond. So a little bit about myself. I am a senior at Millersville University in Pennsylvania. I'm a dual major in physics and mathematics. And again, I worked at the National Institute of Standards and Technology. My mentor for the summer was Dr. Andrei Kolmakov. He really helped me to understand a lot of what I'm about to talk to you all about today. Specifically, I worked in the advanced electronics group. I was even more specifically working with diamond. So why was I working with diamond? Why am I trying to put it into electronics? So first of all, diamond has the highest thermal conductivity of any material on the planet. It is excellent at dissipating heat, which is very important with electronics. It also has great resistance to radiation damage. So any kind of electronics on, say, the International Space Station are constantly subject to lots of cosmic radiation. Diamond has fantastic resistance to that. It also has very high charge carrier mobility. So positive charge carriers, negative charge carriers, electrons move very easily through this material. Coupled with a high breakdown voltage, it can also take very high power inputs, makes it a very robust material, fantastic for electronic applications. However, in nature, diamond typically acts more as an insulator, classified as a wide bandgap semiconductor. It functions more closely to an insulator. So how do we get around this? How do we increase the electrical conductance of diamond? So typically what's done with materials is something called impurity doping, where you introduce foreign materials, a foreign element, into a material's crystal structure. This is typically done to increase charge carrier concentration and increase electrical conductance. However, there are challenges for doing this with diamond. Specifically, diamond has a very tightly knit carbon lattice. It forms very strong chemical covalent bonds. So it's difficult to introduce foreign elements into that. Also, when you do this impurity doping, it's typically done in these plasma reactors pictured there. And when you do this, you often damage the surface of your material. And this is not what we want. It creates lots of hills and valleys on your surface on kind of the micrometer level, which interferes with charge carrier mobility. So how do we get around this? We do something called transfer doping. And transfer doping begins with something called hydrogenation. Specifically, what we do is we want to take our diamond sample and bond hydrogen to the surface of it. Once hydrogen is bonded to the surface, it kind of pulls electrons up and out of the material so that they sit on the surface. Once that's done, an appropriate acceptor material is placed in close contact with the diamond surface, and then those electrons jump from the diamond surface to the acceptor material. And once that happens, it leaves holes on the surface of diamond, creates what's called a two-dimensional hole gas. Essentially, all these positive charge carriers are sitting on the surface. In even simpler terms, it basically creates a semiconductor on the surface, a p-type semiconductor. The physics of this is called band bending. I have a diagram of it on the right there. You can kind of see the valence band of diamond. So the outermost electrons attached to atoms, that valence band kind of bends upwards towards the conduction band of the acceptor material and leaves these holes on the surface of diamond. So how do we actually accomplish this? Well, it starts with a furnace. Essentially, what we need to do to accomplish hydrogenation is a process called annealing, where we expose our diamond sample to very high temperatures of around 800 degrees Celsius. And once the diamond sample is in the furnace, we run hydrogen gas through our system. A turbo pump is connected to that to ensure a constant flux of gas through the system. And these treatments typically last for about 48 to 72 hours. It's a very soft method. Physically in the lab, pictured on the right is our setup. You can see the furnace in the center there. There's kind of a glass tube that runs along it. Inside of that glass tube is where our sample would be placed. And how do we actually check to see that hydrogenation was complete? How do we look at results? Well, we use our 2-probe setup, which I have pictured on the left there. You can kind of see the probes that touch the surface of the diamond, as well as a 4-probe setup, which I have pictured in the center there. So then how do we look at results? How do we know that what we did was successful? Well, for our 2-probe method, we look at ohmic versus non-ohmic behavior. Ohmic behavior would be an example of success. That's what we want to see. We want to see that our diamond sample is now conducting. So on the right here, I have an example of an IV curve. So voltage is on the x-axis, current on the y-axis. And if you look in the bottom left of the graph, we see very straight linear behavior. That's an example of ohmic behavior. It's what we want to see. This is an example of a trial we did where our sample was conducting. We were successful. For our 4-probe method, we wanted more concrete numbers, concrete values, and we used the formula pictured at the top there to get values for sheet resistance, which some of our best data was in the range of about 700 to 1,000 kiloohms. And ideally, we're about an order of magnitude off of some of the best data. Best published data is around 70 to 100 kiloohms. However, this is progress. These are some of the first experiments that we've done at NIST. The setup that I showed you, none of that existed before I came to NIST. I built all of it with my mentor. And so this is a great starting point, essentially. And we also ran into several challenges along the way. We hypothesized that the roughness and the quality of our samples could be affecting things. Like I mentioned, the kind of hills and valleys that exist on the surface, on the micrometer surface of diamond. We also hypothesized that the gas purity that we used, like I said, we used hydrogen gas. We exposed our diamond sample to that. If there were oxidative impurities in that, so if there was oxygen in that, it could affect things, as well as the time allotments for the treatments. In the future, you would ideally perform lithography. So if you had a sample that was conducting successful, You would make electrical devices out of that. You would make field effect transistors, as well as many other devices. You could also perform something called Hall measurements, where you could get more concrete values for charge carrier concentration, mobility, and you could compare those to contemporary materials. And lastly, I'd just like to acknowledge my mentor, Dr. Kolmakov. He was exceptionally patient and helpful to me throughout this experience, as well as the NIST IT department in the early weeks. AIP and SPS for creating this opportunity, as well as my fellow interns for being fantastic people. Thank you.
So the picture that you showed with the two-point probe thing, you made it look like a diamond was a square thing.
Mm-hmm.
Are your diamonds square things?
Yes. We used our samples were usually about 2 by 2 millimeters.
2 by 2 millimeters.
Yeah.
But how thick are they? Deep are they?
Thickness isn't something we looked at too terribly, although all the samples we used were very, very close to the same thickness, about, again, 2 millimeters, thicker than 2 millimeters, around 10 to 20, I believe.
Quick question.
Yeah.
So when you're implanting, when you're doping, how deep does the doping go?
The transfer doping?
Yeah.
Yeah, so that occurs very much just on the surface. It really does not penetrate into the material at all. We're just looking for that phenomenon that I mentioned, the two-dimensional hole gas. So really, we don't really care about how electrons move through the rest of the material. Just we really want to use the surface, which is where, like I said, lithography would be performed on just the surface of our
It's
material.
not impacting the substrate.
Yeah.
Right. Round of applause for our speakers.
All right, next we have our Space Telescope Science
Are you
Institute
on
Research
PowerPoint?
Intern, Tiffany.
All right, thank you for the introduction, Kayla. I'm very excited to share with you all what I have done this summer with my mentor, Dr. Nimisha Kumari, about the Muse HUDF Data Release 2 galaxies. So first, to give you a brief overview of my talk, our goal was to study the properties of high redshift galaxies using the Muse Hubble Ultra Deep Field Data Release 2 dataset, and we are going to analyze the different scaling relations between physical properties. So first, let me introduce you to the instrument Muse. So Muse is a ground-based integral field spectrograph located on the Very Large Telescope in Chile. And it does integral field spectroscopy, which combines the power of spectrum and imaging. So you could imagine taking a 2D picture in the sky, so this is all spatial. And on the third axis coming out, you can get all the different spectral information. So it integrates over different wavelength ranges within this image, and it creates a 3D data cube. Now this survey has 3 different properties. It has 3 different deep fields: Mosaic, UDF10, MXDF, all with different areas field of view and a different integration depth in time. So what that does is it can detect fainter galaxies, and it's very sensitive as well. So Muse itself has a spatial resolution of 0.55 arc seconds at 7,000 angstroms, and it also has a high redshift confidence. So once again, this allows the instrument to detect fainter, higher redshift galaxies. And to give you an idea of just how useful this is, on the left-hand side, we have a UV image from the Hubble Space Telescope. You can see in the contour that there is a light source. Now, Hubble is indicating that this light is coming from just one object. But if we look at the middle and right images, those are the same, it's like the same place, also in UV by Muse. And Muse detects 2 different sources at 2 different redshifts. So one of them is an O2 emitter, the other one is a Lyman alpha emitter further away. So this provides us a really good opportunity for studying the rest UV properties of high redshift galaxies. So to analyze these properties, we are looking at various relationships between stellar mass, gas phase metallicity, star formation rate, and redshift. And for our lines of interest, if we look at the little window to the right, that is an example of a galaxy that we used in our sample. We can see all those vertical lines are our lines of interest, Lyman alpha, C4, helium-2, C3. So we wanted to select a redshift range where all of these lines are covered within this wavelength window. And that so happens to be around redshifts of 2.8 to around 4. And in order to ensure that we're getting the best data possible, we are limiting our study to galaxies with signal-to-noise ratios of higher than 3 and a high redshift confidence as well. So after a lot of sifting, our total sample came out to be 121 galaxies. And what we want to study is the Lyman alpha signal-to-noise ratio greater than 3 galaxies. So I have on the bottom there a lot of histograms of all the different lines that we are interested in. In the dark blue, those are the amount of galaxies that we want to study. So for the Lyman alpha galaxies, or the lines, you can see that there's a lot of deep blue. But for the other 3 lines, there are only 3 to 4 galaxies that have those lines. So because of this small sample, we are unable to study in depth the correlations based on C3, C4, and helium-2. But what we did look at was, for example, mass versus magnitude. On the x-axis, I have stellar mass, and on the y-axis, I have the magnitude in UV. And we found an anti-correlation because there's a downward slope. So as mass increases, the galaxies are getting brighter in UV. And all those different color dots you're seeing represent redshift. You can see that the blue and red are kind of scattered all along. So in that sense, we can say that there is little to no correlation with redshift. And this happens so to be the case with a lot of the other relations that we are looking at. The next thing we are looking at is the mass versus star formation rate of these galaxies. We found a positive correlation, which means that the massive galaxies have higher star formation rates. I would like to also point your eyes to the top line in the blue. That is a line describing the star formation rate of local analogs, and those are galaxies around redshift of 0, so very close to us, that should be comparable to high redshift galaxies, like around redshift greater than 2. And on the most bottom line, that is high redshift galaxies, like around redshift greater than 2. And on the most bottom line, that is a line describing the star formation rate of the local main sequence galaxies. So how does our sample compare to these 2 lines? Well, our sample in the dots have a higher star formation rate than the local main sequence galaxies. This is as expected because earlier galaxies should have a higher star formation rate than the local galaxies. However, our sample has lower star formation rate than what was suggested as local analogs. So what does this mean? It means that the galaxies suggested before are probably not local analogs of higher redshift galaxies, at least for our sample range of between 2.8 to 4. Another thing we looked at was the mass versus metallicity. So looking at the plot here, on the y-axis, I have gas phase metallicity, and on the x-axis, I have stellar mass. And we estimated this metallicity using 2 different tracers suggested by a previous paper in 2022. And in the dots on the bottom, those are estimated using the equivalent width of C3, and on the top is using the C3-O3 ratio. We can see that there is a clear offset, so which estimate is correct? We see that there is a higher correlation of the C3 and O3 ratio, and it fits closely with a fit from before that was consistent with data sets and a lot of different studies. However, this can be taken with a grain of salt since we have a very small sample. You can see only 4 galaxies are being compared here, so it could just be pure luck. And I've said a lot, so to sum everything up, in our study, we explored the general trends of galaxies between redshifts 2.8 to 4. We also saw how our sample compared to the local analogs of high redshift galaxies. For our study, we had a very small sample of C4, C3, helium-2 lines that are signal-to-noise ratio greater than 3. So we want to see if these lines are indeed common at high redshifts. And if they are, we can study those line ratios to uncover the physical properties of galaxies and ultimately understand the star formation in early galaxies as well as in their environments. And these are my references. And I would like to thank my mentor, Brad, Kayla, Michaela, and all the SPS interns for this amazing summer. And I can take questions.
Questions?
So you said that you only use galaxies with high redshift confidence, and that you use galaxies where the spectral lines that you want to observe fell within like the spectrum that fit with your 7,000 angstroms. Is there any reason, like how did you choose which redshifts? Like where did you get your redshift data from, and how do you know that it's high confidence for this?
Yeah, so the Muse HUDF data release actually is like a catalog because it's like a survey of a lot of galaxies, and I sifted through 1,301 Lyman alpha emitter galaxies, and I actually just went through all of them. I made all the spectra, and I was like, which lines are here? And I selected the redshift range where all of those lines are enclosed. And it's really good to look at them because those lines are in our local galaxy and are useful to study the UV properties of our local galaxy. So we wanted to look at, okay, is this also usable for further galaxies?
So it was you're the redshift database.
I am the redshift data. Well, Muse is. Yeah.
Question in the back.
Thank you for a very interesting talk. I was wondering, why were you so interested in those particular 4 spectral lines that you mentioned?
Yeah, so Lyman alpha and C4, helium-2, C3, those are, I read a lot of like different literature prior, and those were kind of the lines that they used to study the properties of star formation galaxies and also just how the galaxies evolve over time. So studying these lines can help us study more about how galaxies formed in the past and relate to how they are formed today.
Can I ask one other?
Yes, please.
It was very interesting. So what does it mean to be a local analog? How did they come to that conclusion first, and you basically shown that they're not?
Yeah, so a lot of studies are actually studying what galaxies we can use locally, like within our little redshift range or younger galaxies. They want to see how we can use these galaxies to study the past. So that's why it's kind of useful. As for how they got the data, they kind of just used another survey, and that's what they are hypothesizing is relating to the past. Yeah.
Round of applause for our speaker. Great talk. Okay, let's get you up.
Next, we have our
Where you at?
AIP
Where you
Center for
on?
History of Physics and Niels Board Library Archives History Intern, MJ.
That's a PDF.
Mhm.
Okay. Oh, it's thinking. All right. Oh, my font didn't save. All right. Hello, everyone. My name is MJ, and I was the AIP CHP NBLA history intern for this summer. Now that you've had your review of the alphabet, a little bit about me. I am a junior at the University of Rochester. I study physics and astronomy, and I'm a music minor. I do dark energy research, and I'm an orchestra member. I'm originally from Tampa Bay, Florida, and I'm a lifelong library lover, so I was really excited to get this position. At CHP and NBLA, I focused very heavily on improving visibility of underrepresented physicists in history and today, which means that my research focused very heavily on these underrepresented physicists, including racial, ethnic, and gender minorities who very commonly struggle to receive recognition, even on sites like Wikipedia, where the majority of articles that exist are of white men, largely from the Western world. In my research, I also ended up focusing a lot on white men, largely from the Western world. In my research, I also ended up focusing a lot on atomic theory and the development of our understanding of the atom. And in addition to all of this, I took on a couple other side projects. So instead of just telling you about one specific thing I did, I'm going to take you on a walk through the entire history of atomic theory in the next 5 or so minutes, covering all of the major developments and all of the work that I did related to those developments. So we start in 415 BCE, with Democritus, the laughing Greek philosopher, who was the first to propose a theory of atomism, where he said that there's something tiny that makes up everything that we see, and they're all connected to each other. He got that part right. Related to this, I wrote a blog post called Atomic Theory in Antiquity for Ex Libris Universum, which is the Niels Bohr Library and Archives blog, and that post will be going up at the end of this month. Jumping almost 20 centuries into the 1800s, we meet John Dalton, who was a meteorologist and chemist who used his understanding of materials in the atmosphere to say that different atoms make up different types of materials. So he saw that there were masses of oxygen, he didn't know it was oxygen at the time, moving, and masses of nitrogen moving, and said, hey, these are made of two different things. I wonder if we can work with that. Following him, we met J.J. Thomson, who proposed that there might be something electronic happening inside of the atom, and he verified this with what was known as the cathode ray experiment, where he launched cathode rays, which we now know are called electrons, through a tube of gas and observed what came out the other side. If you look in the top left of all of these, you can see his first model of the atom, which is a massive solid charge with electrons scattered throughout. If you've heard of the plum pudding model, he was the guy who did it. Following him, we meet Robert Millikan, who was the first man to quantize both the mass and charge of the electron in one fell swoop, based off of J.J. Thomson's discoveries. If you look at the picture in the top middle, you see two men, Thomson on the left, and his eventual companion, Ernest Rutherford, who launched a bunch of alpha particles, which are tiny charged particles, at a really thin sheet of gold foil, where he expected that they would all just pass straight through because alpha particles are really small and known to penetrate things. But rather than doing so, some of them deflected at super high angles. Based off of this, Rutherford theorized that there's something really dense in the middle of all of these atoms. Rutherford restructured Thomson's model of the atom and said there's something called a nucleus, which is super dense and super tiny at the very center, and it's surrounded by an almost empty cloud of electrons. All of this information I've condensed into a teaching guide called The Evolution of Atomic Theory for the Center for the History of Physics that'll be going up also at some point later this month. Teaching guides are 1 or 2 day curricula that a teacher from a school anywhere in the world can download, and they come with an entire lesson plan, student activities, extensions, related teaching guides, all of the information you need to impart this knowledge on some students. So this one is designed for about high school age students, but I'll probably be giving it as a little seminar to my college classmates. We continue into quantum mechanics. In 1913, Niels Bohr remade the standard atomic model based on his assumption that the electron was both a quantum object, meaning that it operated as a wave, and a classical object, meaning it operated as a particle. Based off of this, he came up with what we know as the Bohr model, named after himself, with a solid nucleus and then rings around it that show the electrons traveling in distinct orbits with distinct energies. At the same time, back in the classical world, a man named Henry Moseley reorganized the periodic table based on the charge on the nucleus. Prior to this, the periodic table had had a little bit of organizational trouble because it had been based solely around the atomic mass. After Moseley's reorganization, he theorized that there were elements that we were still missing on the periodic table, and a search set out to find these. If you see the 3 individuals in the top right, from left to right, that's Jane Dewey, Elizabeth Laird, and James A. Harris. James Harris was the first African American to discover another atom based off of the theories that Moseley developed for what might be missing. I wrote an article on these 3 individuals who you probably haven't heard of for the CHP November newsletter, covering their discoveries, their relation to the names that we've been covering in our atomic history, and the work that they've done that's continued on into today. Jumping a little bit further ahead to 1926. Oh, I forgot. I also wrote a blog post about the process for finding these physicists, which really involves a lot of looking through the related links on Wikipedia, which I highly recommend if you've never done. And in 1926, Erwin Schrödinger expanded on Bohr's idea of the atom, saying that not only is it a quantum object, we can't even tell where the electrons are in space. We only know the probability that they might be in some specific region. A little bit more on quantum mechanics. Up top is Niels Bohr, the namesake of the library that I've been working at, lecturing in Copenhagen. And throughout the 1930s, the biggest developments in science were largely in quantum mechanics, and they were scattered all over the world, including right here in Washington, D.C. If you see the map in the bottom right, that is an interactive map that you can go to aip.org/xlibris and view my photos of the month post covering scientists who worked in Washington, D.C. and the actual locations where they worked. Jumping through World War II, we meet Charles E. Anderson, who was a Tuskegee Airman, who was one of the first meteorologists to train at the Tuskegee Airfield. And in 1960, he received his PhD in meteorology, becoming the first Black individual to do so, not just in the US, but in the world. Based off of him, I made another teaching guide, Meteorological Forecasting Like a Tuskegee Airman, designed to train middle schoolers and younger high schoolers in how to understand a meteorological forecast, how to read a pressure map, and how to make their own. This can also be found online. And now we get to today with the 1960s, the creation of the laser and advancements in optics, where at the far right, you can see I made some book displays for NBLA based off of our collections. And now there are still physicists doing great work all over the world, but a lot of them haven't received recognition. So I hosted a Wikipedia edit-a-thon for all of the interns you see in this room and on the screen to add information and update headshots for individuals on Wikipedia who were missing information. I then took on an additional project to contact still living underrepresented physicists to obtain their headshots, and I've uploaded over a dozen of them to Wikipedia that didn't exist there before. All in all, I grew a lot of my research skills, especially my reading skills. I made some incredible connections with people at AIP and libraries. I read a ton of new material, including primary sources from the great physics discoveries of the world, and I wrote over 12,000 words that are going to be published throughout this summer. I want to say thank you so much to my mentors, Corinne and Joanna, who is here today, everybody at NBLA and CHP, and all of the other interns here. And you can find my work at aip.org/xlibris, history programs, CHP's November newsletter that you can subscribe to, and in NBLA. Thank you. Hello.
Did you sleep this summer?
More than you would expect. Yeah.
It's a tremendous amount of work. Great talk.
Yeah, it doesn't feel like work if you're loving what you do.
So I did have a question before, and it's gonna come to me. Oh yes, did you look at the web exhibit?
I did.
On
Rutherford.
Nuclear World.
I did, yeah, it's
So
gorgeous.
How did that help you in your research?
It didn't end up playing into what I did much because I chose to focus rather than on information that we already have kind of digestible and available for my atomic theory teaching guide. I focused on the primary sources, like the actual publications that presented these ideas. So I went and found Rutherford's publication in Philosophical Review and included that. But it definitely informed a lot of my love for this era of physics because I already was a huge Niels Bohr fan before I came to intern here, and now I love him even more and a lot of his contemporaries.
Quick question at that. Yeah, a lot of really great work. Just very quick question, all the way back to the beginning. Why was Democritus the laughing philosopher? Did it say anything about the mood of all the other philosophers?
It was a nickname that was given to him, and it's been his primary depiction in art. We don't have any of his primary sources left, but all of the secondary sources that kind of describe him as very jovial and very curious. So I thought that was a fun little fact. And you can look up some positively unsettling art of the laughing philosopher online. All right. Thank you so much.
All right, closing out the first half of our presentations is our SPS SOC intern, Emily.
I'm just going to enable something, so hopefully my presentation works, and then I'll get myself started. Yay. All right. Hello, everyone. My name is Emily Pavasars. I am the SPS SOC intern, and I am from Valparaiso University in Indiana, and this is my summer of outreach. A brief warning, there are interactive portions of this presentation, so mentally prepare yourself when I ask you a question. So first, we're going to meet the team. So I worked with Brad Conrad, the SPS and Sigma Pi Sigma director, and Michaela Cleaver, who is the SPS program coordinator, and they were awesome, and I loved working with them so much. So let's walk through what I worked on this summer. So first, I worked on planning and organizing the Astronomy on the Mall event for SPS. It is the largest astronomy outreach event in the world, and there were 100,000 people who attended this year. Second, I updated our Physics Jeopardy, which is a fun tool for SPS chapters to use to host fun events for their members. I also updated our demo library, adding some more outreach demos for those chapters to utilize within their own communities. And I will provide 100 schools with a SOC kit, which is actually a redundancy. It's the Science Outreach Catalyst Kit. So I will provide 100 schools with these kits surrounding the eclipse. So moving on, like I said, Astronomy on the Mall is the biggest outreach event in the world. We were one of the 66 institutions that attended. We had 3 tables with we had about 7 demos that we did, and we taught about 100,000 people science, which was focused on those K-8 kids and their families. So here are the demos that we focused on. Pictured here is the Fabric of the Universe demo. It is a gravity well demo. So if you see those big spandex rings and you get like marbles and you throw them around, everyone loves this demo. It is super fascinating to watch. And I know that we lost at least 5 marbles somewhere. So I don't think anyone got injured. Another highlight was the trivia. We had 21 pounds of candy that we brought to distribute to people to maybe bribe people a little bit to playing trivia, and we got rid of all of it. And a special thanks to Dr. Gary, who is pictured here, for coming and providing adult moral support for all of us. Next up is Physics Jeopardy. This, like I said, is a free tool. And this is our interactive portion. So this is the tool for our SPS chapters to use to host those fun events. And the theme this year is the AIP member organizations. So this is what it looks like. We're going to pick APS for 300, which is the American Physical Society. So we'll go through this. So one of Maxwell's laws does not have a name. What is it? Does anybody know? Tiffany. Is? What's it equal to?
0.
There you go. So, ta-da! Good job, Tiffany. Very proud of you. So yeah, Physics Jeopardy is an awesome tool. I know my chapter has used it within our own community. So moving on to our demo library, this is an example of what you'll see. My demos are now fully updated. I created 3 of these demos and uploaded them. So with these demos, you get a video to show you how to teach you about the construction of the demo and to like show you what the demo actually looks like, and along with a full write-up. So this gives you what you need. This talks to you about like how you can explain this to people at different age ranges, and teaches you how like difficult the science might be behind it. So we're gonna watch one of these videos. Hopefully it will play. Yes. So this is one of the demos that I did. I don't think there's going to be any sound. So this is part of the construction part. So you get to see all the tools that you need. And then you will watch this little video. I had a ton of fun editing these videos, and it was a bit chaotic trying to film them, as some of you can attest. So this is what the demo actually would look like in person. You get to watch as the planet deforms just a little bit due to the rotation. So moving on to the capstone of my research here is the SOC, which is the Science Outreach Catalyst Kit. And this year's theme is eclipses once again, because we have 2 eclipses coming up in the next 365 days. There is one on October 14th, and this is the annular solar eclipse. And there's one on April 8th, and that is going to be our total solar eclipse where the sun completely covers, or the moon completely covers the sun. So the goal of these kits is to provide a full table setup so that SPS chapters can do outreach, so that you can just take this kit and then you have everything you need to teach people. And like I said at the beginning, I created 100 of these kits. So included in this kit are some awesome demos. So the first one I actually brought some for people to see is the soda straw rocket. So you'll be able to create a rocket like this made out of paper, and you get a straw and you can use it to shoot the rocket. I'm not going to do it up here, but this is a ton of fun. I know that you can use it to study forces and momentum, projectile motion, stuff like that. Planet deformation, which you just saw the video for, is used to study how the rotation of the Earth deforms the Earth just a little bit, causing a little bit of a bulge around the center. And then, of course, if your theme is eclipses, you have to explain how eclipses work. So this is one of our balls. This would be the sun in our demonstration, and you can use it to set up a little demo, just to tell kids about how the eclipses work, but we can also use it to explain how scientists detect exoplanets and how scientists detect companion stars. So this is me with all 100 kits that I packed this week. Also included are some fun things. So solar filters, of course, for solar eclipse safety. I designed some SPS cow stickers, which are actually on your tables here today. They are free for you to take. Along with that are some table cards, which explain the science and give a bit of more information for people when they come up to look at your table. Some bubbles, because who doesn't love bubbles? And then some thumb drives, which contain copies of all the write-ups, videos, and table cards that you need, along with additional eclipse safety information and articles providing resources for those students. And then honorable mention, I created 2 shirts this summer. Pictured here on the leftmost pictures are all of us heading to Astronomy on the Mall with the intern and mentor specific shirts. And then I created a shirt just for the interns to remind us all of our awesome time here. And you can see the design on the bottom and the little cow that the design team is I'm very grateful for them creating our little cow for us. And that is my talk. Thank you so much for listening to me.
Questions? What was your process for deciding what to include in the talks?
So we decided our theme pretty early on. We were like, okay, there's 2 eclipses coming up in the next year, so let's choose that. And then Janessa was our SOC intern last year, so I looked at what she did and I was like, okay, these are some great ideas, but I don't want chapters to have the exact same kit as last year, so let's see what we can go off of there. And then I spent a lot of time on Google putting in science for kids, science demos for kids 12
You can like see yourself here. I did not realize.
Oh, I know. I hear my name
Yeah, I didn't notice it earlier. All right, we're going to go ahead and get started. All right, Erin, are we